second part, nobody actually has done factory or rather complete, so I have not considered that. So I have considered only for 15 marks. So those who are here, they can given summary. Nimsha is not there. Rani is also not there. Farhan, Akhil Kumar Jha, Subhan is also not there. Chandran Naidu is also not there. Abhishek is just okay. So anything you have to discuss regarding quiz or tutorial or anything? In each column, right. So you will calculate Q versus delta. You will plot for individual assemblies, and then you will add entire. That will give you Q versus delta for one story. Then you will add for different stories in the series.
Means when we calculate this assemblies, we have to apply the force here. That value of force will be Q over Q.
This confusion is always okay. So when we are doing this, for any assembly we are applying. So what is this Q? When I write Q, what is this Q?
Column force.
How much is this?
Storage here, this way.
So how much is this? In a building, let us say this assembly I have. Okay. In this assembly I have shown Q, I have shown Q here also, or I can show this as V or anything. Okay. So what is this Q? Which value?
That Q by that
Force
Q
in
by
column. Force in column.
Force in column. How much will be that?
It depends upon the distance of column.
No, sir.
Ah.
This force Q is the capacity of the structure when the structure going to fail. We are first forming the hinges at a location where VCR equal to 1. Then we are moving to that Q. From capacity to capacity, we are moving to that.
So when you are plotting Q versus delta, so what is this Q?
This is the capacity.
So it is just a representational force that we are using when it goes to yield. So it is actually equal to the capacity of.
So is it yield force, it is ultimate force, which force?
This is ultimate force that can apply on the structure. So that
Just ultimate force, not yield force.
because corresponding.
What is this force?
This can be ultimate as well as it depend on class.
Depend on
So what value it will have? It does not have any unique value. It is a variable. So you have this curve. This curve gives you the relationship between Q and delta. So it is relationship between Q and delta what you are getting. You are not getting the value of Q. Okay. So this is general. This will also have Q. This will also have Q. This will also have Q, and still this can be Q. Because this is variable. This is general. So when you will be adding, the distribution will automatically come into picture when you will be adding those in parallel. Okay. So we are not adding Q. We are adding their capacity curves. So when we are adding the capacity curve, so at any given displacement, whatever Q we are taking from the first assembly, second assembly, third assembly, that will be automatically added. So this is a variable. All the assemblies can have Q. So you need not to subdivide those when you are doing this method. You need not to subdivide the story shear into different columns. That will be taken care of by parallel and series addition automatically. So this Q is variable. Every assembly will have Q. Okay. So you need not to take Q by 3 or 2Q by 3. You can't in fact do that. For that you need to know the stiffness, and that will be valid till our structure is elastic. It has not yielded. Okay. So there is no need to obtain the value of Q. We will be obtaining Q versus delta for this assembly, Q versus delta for this assembly, Q versus delta for this assembly, which is giving strength or capacity of our assembly. Okay, and that capacity we are at. Capacity is not given by one value, rather capacity is given by this curve. So what this curve is representing? This is representing strength, this is representing stiffness, this is representing ductility, this is representing post-yield stiffness. So all those are given by this, and that we are these capacities which are given by this curve, Q delta curve. Those capacities we are adding. We are not adding Q. Okay. So this Q is just a general variable. Do not try to calculate the relationship between Q in different assemblies. Okay.
Sir, but whenever beams were rigid, in that case we have.
There we are not doing. When we are doing that, we are not using here. How we are doing this parallel and series addition? By satisfying compatibility. Okay. When we have done this, you could have done there also in the same manner. Okay. But we have used a different approach here. Because here it is easier to compute the stiffness of these, elastic stiffness of these. So what we did, we calculated if this force is Q, so in proportion to that we have calculated. Okay. So here also we have used compatibility. But we have used compatibility at a different step. Okay. Here we have used compatibility in the beginning itself. Because compatibility means what? The displacement is same. And if the displacement is same, the force will be in proportion to the stiffness. So if you know the stiffness, you can distribute. Okay. There, the same compatibility when we are satisfying. We are satisfying at the end when we are combining different assemblies in parallel or in series. There we will be satisfying compatibility. So both are same, but here it is done in the beginning, there it is done at the end. So that distribution in different assemblies will be taken care of when you are adding them in parallel. Okay.
Sure.
Alternatively, you can consider this also as one assembly and this another assembly. You can put them in parallel. Then also you will get the same thing. That's just alternative way of doing the same thing. Yes, Ivan.
Sir, we add the parallel combination after that for the particular story. because principle of superposition is this, that's why we have to add.
We are not using principle of superposition. We are using compatibility. Principle of superposition is different. Principle of superposition is that the structure is same. On that you apply first one load, then you apply second load. Calculate the response in the first load, calculate the response in the second load, then add. And this is valid only for linear elastic effect. So in our case, principle of superposition is not valid. We are not using principle of superposition. We are rather using compatibility. And compatibility says that the displacement of all the three assemblies is the same. And when the displacement of all the three assemblies is same, it is as if those are connected in parallel.
So, yes, in this portion, in this forming at this top, when I have to calculate delta u, for that calculate delta p, but when for delta u, this will test to theta u ultimate. Okay. This will not cause any that additional deformation because change is forming here. When it is rotating here, there is no one here to get deformed. It should be for that delta you should take on.
So you are saying the question is that in this case, let us say the hinge has formed here. Okay, so before formation of the hinge, it was deforming like this. So then hinge formed here, and after formation of the hinge, it will deform in the additional displacement beyond this. It will be like this.
Yes.
Like a cantilever. Okay, because it is here. So what is your question?
When you apply the load, you can take load because
Yes.
bottom hinge is not formed here.
Right, so it can still take some load.
But it, for delta roof, there should not be delta u due to ultimate rotation of first hinge.
What is delta roof? Delta roof is this plus this. So delta 1, or we have used delta superscript and delta 2. So delta 1 will become to delta 2 will calculate, that will be roof.
Delta will be from bottom story.
No, this is I am calculating only for this story. Okay, you have to add because here also some deformation will be there in the first stage, and there will be deformation in the second stage also. So let me call this as delta 1 in 1, this as delta 1 in 2, and this as delta 2 at 1 and delta 2 at 2, and delta roof in step 1 will be delta 1. And in step 2, delta roof, I mean after step 2, it will be so what is the confusion?
Question is that if I am considering this as this, formed here, then
Hinge is formed here.
at bottom, then it can go up to theta u.
Right.
Due to that theta u, there will be delta u.
Right.
If hinge is formed here, if it is going to the theta u, then when does it form delta u? No, not.
Delta U is not above. Delta U is below. So if the hinge forms here. Okay. Suppose already there is a hinge and it is deformed. So what is theta u? Theta u is this angle.
Yes, theta u is that angle. Due to that theta u, there will not be any deformation.
Why not? Without this deformation, how can you make this angle? Without shifting the top, can this angle occur?
No.
So this will be always associated, let me call it theta p. So without this displacement, delta p, there cannot be a theta p.
And that will be delta p equal to theta p into h.
You can see this is linear because it is chord rotation. So this is linear. So this will also be theta p. And this height is h. So from the triangle, right angle triangle, you can see that delta p is theta p into h. So your confusion was because you were considering theta p something like this.
Ah, yes.
So theta p is not above only. Okay, theta p, if there is a hinge, so what is theta p? Whatever rotation this top one may move, okay, then this is also theta p. Another case, the top one does not move, the bottom one moves, then also this is rotation at the hinge. Okay, the top one may also move and bottom one may also move. Then this is theta. So wherever this hinge is forming, the angle is between those two segments. Okay.
So second.
Sir,
Come.
in this case, where theta p is equal to theta p is equal to
Right.
So theta p will be dependent on the hinge which is governing hinge.
Good and bad. Governing hinge. In this case, I have shown only one hinge
Yes.
and one beam.
Yes.
So there is no other one part. There is no other hinge.
First hinge is forming on this.
Right.
And then hinge.
Right.
So delta rho practically I have now delta rho 1 plus delta rho 2 plus theta p into this.
Right.
This theta p will be for this hinge because minimum of the two hinges.
You will calculate plastic deformation in each hinge. Let's take this case. Suppose this is the case. So how the hinges will form? In the same sequence. First it will form here, then here, then here, and then here. So our Q versus delta curve, I am not considering the plastic rotation capacity yet. So our curve, first hinge will form, then second hinge will form, then third hinge will form, then fourth hinge will form, and then it will become flat. Okay, so here the first hinge is forming, first yield, second yield, third yield, fourth yield, then it will become flat. Till then it will continue to take forces.
Can this be the case that when fourth is forming, first one is already.
I am coming to that. Okay, this is when my hinges have infinite plastic rotation capacity. I have not yet considered the plastic rotation capacity of the hinge. Okay. Now, how I will consider the plastic hinge rotation capacity? Let us say my hinge 1 has a plastic rotation capacity of 2 theta p. Hinge 2 has a plastic rotation capacity of theta p, and 3 has theta p, 4 has theta p by 2. Suppose different plastic. How you will do?
Each case delta you have to define.
Yes.
And that delta you should not exceed.
How we will calculate delta in each case?
Delta y plus that theta p into
Which delta y?
delta y of that corresponding case q1 or
Wherever the hinge is forming. So what you will do? This plus 2 times theta p into h. Okay. Second case, this plus theta p into h. This is possible that this is higher than this, or this is higher. Whichever is occurring first, that will control. Maybe delta p plus theta by 2, theta p by 2 h, that may govern. So we have to check the plastic rotation at each plastic hinge, and whichever is reaching its plastic rotation capacity first, there our structure will collapse.
So if you given equation who is same for all the elements,
Right.
so wherever the first plastic is formed, can we say that two will be
Wherever first plastic hinge will be.
formed? That element will be
Actually, when we define mu, there is an issue. So mu is theta u by theta y. Okay, so theta u is mu times theta y. So mu is same. The problem is theta y also same.
If theta y is in the second inch, theta y is reaching 8, then theta u is important.
If you are considering that, that will be okay. Okay. So if you consider that, then what you are saying is correct. That whichever is occurring first, that is having theta y also lower. Okay. Then mu is same. So in that case, the theta u will occur also first. Okay. But actually, theta y is not defined like that. Okay. Because that way, the theta y itself will depend on the structure. Okay, so you have seen that in reality we define theta p and theta p value is given. AC 41. You recall? So value of theta p are given. Mu are generally not given because in that case theta p itself depends on theta y. Theta y depends on the structural configuration. But theta p cannot depend on structural configuration. That depends on the detailing. Okay, reinforcement. Section. So that's why value of theta p is generally given. I mean, if you see in experiments for AC 41, it is given as constant.
Sir,
Yes.
the theta y is delta y1 upon h, or for that delta y calculation, you are considering that q1 first load when the hinge at first hinge is there found, or this q is q step when the further load is increasing. Which one?
But for delta y, you don't need q.
Because delta we need
Huh?
q1 we need for delta y.
You mean for calculation of delta y?
Yes.
So delta y will occur at some value of q here. So this is our first hinge is forming. So it will happen at some value of q. But for plastic rotation capacity, you don't need q.
Because that whatever I am getting theta u, theta u is 4 times of theta y. Theta y is equal to delta y upon h. Delta y equal to PL cube upon 3.
Right.
For that PL cube
So
upon
for
3,
that value of q, let us say this is q1, this is q2, this is q3. That value of q you have already considered to calculate delta y1, delta y2. So when you have calculated delta y, we have already calculated q, corresponding value of q. So why you need q further?
yes. Then delta y I calculate first. That delta y when I am reached stage 4, still I have to use theta p equal to delta y upon h. That delta y1 is this one, first one.
I couldn't get delta y plus theta p into h. So here q is not coming into picture. Where is q?
When you go to stage 4,
Stage 4 means here. Here.
at last, that
Here.
here, there you want to calculate delta z.
I want to calculate delta u. So that will be this delta y4 plus theta p by 2h.
Theta p by 2 into h. For that theta p, you that should not be theta p by 2h. That should be theta y into h.
Theta y into h. Why? Plastic yield displacement plus plastic rotation into height. That is ultimate displacement. Delta u is delta y plus theta p into h in this case. So you don't need any q here. This does not depend on q. Yes. You think about it. If you still have question, you can ask.
For this same concept, can you do like this? My first one only here,
Right.
second here.
Right.
So my delta y1 is this, delta y2 is this. New theta will be given theta u by theta y. I will find theta u corresponding to theta u. I will find delta u. And if this delta u is exceeding both these values, that will be my delta u.
But that may exceed this value also, which we have at the top.
I have to check that also. If it is less than these two,
Yeah, then you will extend.
I will stop and I will.
Then it will not go to the next value.
I will recheck for delta y2.
Okay. Anything else? Yes. Can we increase the value? You take it like that. Can I increase the value? Suppose 100 to 200 to 200. The second story is first story is like that. I want to increase this thing. So let us say 100 to 100. So it will become 150 here, it will become 300. So it can't. So Q cannot be increased anymore. Okay, so on the same Q, the displacement will continue. Still, starting it to be phase. Suppose you have a building, second story is great, now story is standing, what will you do with that? Either ground story is standing, or it might have been reversed also. The first story is great, second story is great, how do you the last one? The ground story is great, upper story are great. Can you say it is okay? You can't say. Deform shape. Let me protect it. The final where the second story, all the four inches are formed. That is your problem. That is the problem. So what is the problem? I'm coming. I will explain everything, don't worry. So the question is, when the hinges are formed here, but still the plastic rotation capacity is there. Okay, so what will be the deformation? Q cannot increase because hinges have formed. So if you want to increase Q, this Q will, value of Q, if you increase at the top also, it will increase. Okay, so that is not possible. So it will continue to deform like this. And this will be your theta. You will check it with theta.
This
Okay.
is theta.
Hmm?
This is which theta? Theta y.
It is the plastic rotation capacity, okay, plastic rotation after yielding. Okay, I do not know whether this hinge formed first or this hinge formed first. So whichever hinge has formed, because it is possible that here there was already some theta, plastic rotation was occurring there. So that also you have to consider. Suppose this hinge has formed just now, then this will be theta p. Okay, or in this stage, I can say, let us say this is stage 3. In stage 3, this will be theta p. If in the previous stage also any theta p is occurring, has occurred, you add that also to it for checking. Okay,
Sir, here you are considering theta p and theta u as a equal.
Theta p and theta u are not equal. Theta u is theta y plus theta p. So before that, okay. This was our step for increment 1. In increment 1, okay, till your hinge is forming here. So this will be the deformed shape and this will be your theta. This will be your theta,
This will be theta y.
not theta y. This will be theta. At some point it may be theta y. At some point it has not yet reached theta y. So at this node it has reached theta y, but not at this node. This node it is still not theta y. Okay, this theta y will occur later in the next step. So same theta can be theta y at one node, it can be elastic theta at other node, it can be theta p at one node, it can be theta y at other. So this is theta rotation. Whether it is equal to theta y, that will depend upon the capacity of that cell.
But the hinge, the location at which hinge is formed,
There it is theta y.
There it is theta y.
Right. But not at the other. No. Okay. So this is your step 1. In step 2, what will happen? This hinge is already formed. Okay. So ground story is still deforming in the same manner. But this story will deform like that. Okay. And you will join this. So here it will be theta inelastic, let me call, which may not be equal to theta p. Okay. And here it is still elastic. So when the hinge will form here, at that time, this value of theta, let us say previously I am calling it theta 1. Okay. This is theta 2. Okay. So at the okay, so theta 1 is equal to theta y at okay, and theta 1 plus theta 2, these are theta y at okay, and theta 2 will be the plastic rotation which has occurred at 4. Okay. Yes. Your beam is using or column is using in this assembly?
Column delta which is ultimate delta of column which is plus as compared to the floor.
No, but if column leading, if column is not leading, then it's plastic. It is not talking to pictures. Plastic will not be plastic column plastic, it will not talk to pictures. It will be the plastic. It will be the beam plastic. हाँ नहीं बनेगा वहीं प्लास्टिक होगा नहीं बने नहीं वहाँ पे कौन प्लास्टिक ओके यस So this is second step. Hinge has already formed here. So this will become like pin. So if I have this type of a system where at the top there is pin, okay, can it take lateral load or not? You just take two columns and at the top of those two columns you keep, it is not belted, but just to keep it. Okay. Will it not take any load in the lateral direction?
It can take.
It can't take. Suppose there is a cantilever column. Okay, cantilever column you can consider as if it is having hinge also. Still it will be cantilever. Okay, can it take any load?
But here,
No. I will come to that later. First talk about this. Can it take load? Now let us see what is the difference between this and this. Here I have just added one horizontal slab also into it. So will it take load? Still lateral load or not? Now I take two such columns, one over here, add this slab and then connect it. So what is the difference? It is same as this. So when you will, and you also look at it, if you are giving it a deformation and it is possible to deform without developing any bending moment, then it will not take any. But if when you are trying to deform it and bending moment is developing, then to counter that bending moment you have to apply some force. That means force will develop. So try to plot the deformed shape. If you are plotting the deformed shape here, okay, can it deform like this?
No.
It can't deform like this. Why not? Because at the base it is fixed and no hinge has formed. Suppose hinge has formed here also. Then it can deform like this. Then it can deform like this. But because at the base the hinge is not there, it can't deform like this. So it has to deform so if I take the center line, it has to deform like this. And when it is deforming like this, a bending moment is generating here. How this bending moment will be balanced? That bending moment can be balanced only with a force at the top. That means you have to apply a force. Okay? So without applying force, it cannot deform.
Instead of Q, if you apply moment there,
Where?
that Q2.
At the top. So where? At the top.
At joint.
You want to apply a moment like this.
Yes. No, at above that.
Above that joint.
Beam plus column. Because that can understand that hinge can transfer shear force but not moment.
Okay.
If the
So
moment
you
is opposite-
mean you are applying a moment here.
Okay. Then does it deform?
No.
Because
This moment cannot be transferred. But if you are applying a moment here, then it will deform. So this moment is not going to cause any deformation here. But this moment is going to cause. But if you apply a force here,
it can deform.
then it will deform. Because this hinge can transfer shear force,
But not.
but not moment. Okay? Any other question? Sorry? So what is the question? Right. Right. Space. Yeah. After that, what you have to do? That will be your Q versus delta. When you have done both parallel assembly and series assembly, that is the answer. What has been asked in the question? base shear versus roof displacement. So when you will do that, so base shear will be equal to Q. Now, after assembling what we are getting that, the resultant of each story you will calculate, and those resultant you will add in series. Q we don't have to distribute. You people have joined late. Okay. You can solve the questions in two ways. Okay. Either you consider Q in all the assembly. So in all the assemblies you will consider Q. Okay. Then you will add the Q versus delta curves in parallel. Okay, we are satisfying the compatibility. Or like we have done in case of rigid beam, you distribute the Q in the beginning. That is also compatibility. So one of the two you have to do. If you are distributing Q in the beginning itself, you need not to do parallel assembly. Compatibility you have already used. Okay. If you are considering Q in all and then you are combining, so that distribution is taken care of by this parallel combination. You need not to distribute. Okay. So two ways I have given you of doing that. In case of fixed beams, rigid beams, you are distributing Q in the beginning itself because stiffness is known, so you can distribute in the beginning itself. Okay. That is also the same. And in case of flexible beams, we carry out Q versus delta analysis for different assemblies, and those assemblies we are combining in parallel. That also means the same thing. So same Q, this is also Q, this can also be Q. Don't get confused that this is Q, then how it can be Q. We have to divide it into 3. No division is needed because we are doing combination, okay, in parallel. So in that case it is not needed to divide. Yes, for each assembly, first distribute variable force. So it is not a given force which you have to distribute. It is variable. It can take any value. Okay. So this Q here, this is some variable. It can take any value depending on the assembly or the structure. It can take any value. Okay. So it is not having a given value of, let us say, 1000 kN which you have to distribute. It is variable. It can take any value you want. Q can also be equal to Q by 3, Q can also be equal to Q5, Q can also be equal to 102 because it is variable. So this is just a variable. You need not to distribute it. In this case, here we are distributing it. If you have distributed it, then there is no need to connect them in parallel. Okay. So this is a common problem. Every year people get confused that if this is Q, how can this also be Q? It can, because Q is variable. Q is not a fixed value. It is just a notation to show the force. Okay. Yes.
Question 5. Second question. There is no significance of this 2Q and 2P.
That's what I explained. Okay, so what we did, first we plotted story shear. So we plotted the story shear like this. This is 2Q and this is 3. Then we assume that in this portion it is 2Q. In this portion it is 3Q, and in this portion also it is 3. Okay, this is approximation we are doing. Actually, here in this portion it is 2Q only, but we have considered it 3. Okay, to simplify our calculation, it will be slightly conservative. It will give slightly more displacement. Okay, but to simplify our calculation, we have done that. Then you will calculate the displacement of this top story. Displacement versus force. So for the top story, after combining these two some assemblage, okay, you will get the resultant Q versus delta. Okay, this is, let us say, I am calling this as story 1, this is story 2, this is story 3. So Q3 versus delta 3. Okay, so that will be this Q versus delta plus this Q versus delta that you have added. Then you will get. Similarly, you can get for story 2. You can get for story 1. Okay. Now you have to add these in series in such a way that you get base shear versus delta roof. Okay. Now let us say you assume base shear in such a way that the first story is yielding. Okay, so when first story is yielding, then what will happen? If, let us say, this value is 100 kilonewton. Okay. Just some value I am giving. Okay. So when the base shear is, let us say, 100 kilonewton, what will be the value of Q? When base shear is 100 kilonewton, what will be the value of Q? There is a relationship between base shear and Q. So how much will be Q? Base shear is 3Q. So base shear is 100. So Q will be 100 by 3. Okay. So if Q1 you are using 100, how much will be the value of Q2 at that time? Or in the second story, how much will be the story shear? I can also call these as V1, V2 also in place of Q1, Q2. Then it will be so you can see that V1 is equal to VB. isn't it? Whatever is the story shear here in the ground story, that is same as BB. So when BB you have taken 100 kilonewton, here it will be 100 kilonewton. How much will be here? B2. That will also be 100 kilonewton. How much will be B3?
2 times of this, 200 by
200 by 3. So here you will read corresponding to 200 by 3, 166. That value you will take. Got my point? So that's how this relationship between Q and 2Q is coming into picture. It will decide the relationship between different story shear. This pattern, how it is increasing along the height. That will decide the relationship between different story shears. Because when you are connecting in series, suppose force is acting only here. Then all these will have Q. That is your first part, where only one force is acting at top. Then the forces in all the springs will be equal to Q. But suppose I apply a force here also. Let us say I apply a 2Q here, I apply a Q here, I apply Q by 2 here, let us say I apply Q by 4 here. So how much will be this? It has to be sum of all these. Okay? Or let me, for making our calculation simple, let me make it like Q, 2Q, 3Q, 4Q. So how much will be the force here? 3, 3, 6, 10. How much will be the force in this spring? How much will be the force in this spring? It will not be same. Okay? So this is like a story shear. So here it will be 10Q. How much will be in this? 9Q. How much will be in this spring? 7Q. And how much will be here? Same thing is happening in these stories. So each story you can represent by one spring. So forces in all the springs will not be same. Those are going to be different. So story shear in all the stories is not going to be same if the forces are acting throughout the height. If force were acting at the top only, then it was okay. Then same story shear, same force in the all the stories. But here the forces in different stories are different. So what is the relationship between them? That will depend on how this force is increasing. I have increased here Q, 2Q, 3Q, 4Q. If I add Q, 3Q, 6Q, 9Q, then it will be different. Or if I add it parabolic, so Q, 4Q, 9Q, 16Q, the relationship will be different. And this depends on the deformed shape. Okay. Generally, we take it, we will see it later, we take it proportional to first mode. So here I have considered this mode as linear, but the mode can be parabolic also. Okay. Or somewhere in between the linear and parabolic. So later on, when we will talk about pushover analysis, there we will talk that how this variation should be considered. But we understand that during earthquake, there will be certain variation of the force along the height. The earthquake force is not acting only at the top, and it is also not uniform. It will be less at the bottom, and it goes on increasing towards the top of the earth. I also explained why it increases at the top. Why the flow load is more at the top. less at the base. Larger acceleration at the top. Why larger acceleration at the top? So when it is vibrating, let us say in fundamental mode. So at the top it is vibrating more, at the base it is vibrating less. Okay. So in the same period it has to cover longer distance at the top, lesser distance at the bottom. So if it has to cover longer distance, it has to undergo larger velocity and larger acceleration. Okay. So at the top it is going to be more. But storage shear will be always more at the base. Why? Because whatever load is acting at the top, that has to flow down. Okay, it has to come to the ground. So from the top story it will come to the lower story, then from there next lower story, and so on. So flow load at the top may be more, but storage shear will be more at the base. Always. Yes. When Q is positive, let us say this is your positive direction. So when Q is positive, delta will also be positive. Q is negative, delta will also be negative. So the curve will be like this. And actually during earthquake what will happen? It will be cyclic. So it will first go, let us say, this side, then from here, okay, from here it will go like this, okay, then it will, and so cycle. So it will be different on different sides for different directions. Okay. Any other thing you have to ask about tutorial? B delta. So what is this P delta? Okay. Let's start with cantilever again, as we have done earlier. So intentionally I represented this by Q because P I have reserved for action. Okay. So when you give this, apply this Q, there will be displacement delta, and this axial force will also shift. Okay, I have not shown axial force like this. Actually, axial force should be like this, but I am still showing it vertical. How to justify that? Again, this delta is still small. Okay, so that inclination I am ignoring. Okay, so I am considering this P vertical only, but let us say this has shifted.
So can I interrupt you?
Yes.
But this V delta will work on the larger displacement. It's after certain displacement. So at that point, will there be this assumption is valid or not?
We will come to that. Let's assume for the time being that the delta is small. So P delta analysis and large displacement analysis are different. P delta analysis is not large displacement. P delta is just one component of large displacement we will talk about. Okay. So let us say this delta is small, then I can consider this as vertical. Okay. So, but what will be the effect of this P shifting here? there will be one moment here. Applied moment I am calculating, let us say. So one moment will be equal to Q into H. Okay. Plus there will be another moment which will be equal to P into delta. Okay. Now let us say this moment capacity here is M, yield moment, or let me say M1. So will the yield capacity change? It will change depending on PM interaction curve. Okay, but let us ignore that PM interaction curve effect of P we are ignoring. Otherwise, when we are applying P, there will be some change in the moment capacity also. So that we are going to get from PM interaction curve. So we will get that from PM interaction curve. Let us say that value of My I have got here. So now this My will be equal to Q Y into H plus P into delta. Earlier we have calculated Qy, that was equal to My by H. Now what will happen Qy? Qy will be My by H minus P delta by H. So yield moment capacity is same, M1, but the lateral force at which the yielding is occurring has reduced. Okay. Now what will happen to delta Y? What will be delta Y? Will the delta Y change or it will remain same? How we obtain delta Y? And how is phi y? My My value is not changing. Okay, and let us assume that this column is steel to begin with, not RCC, because in RCC EI effective will change. Okay, but with that we are not considering. Let us say it is made of steel, then EI is not going to change. Okay, so My does not change, EI does not change, H does not change. So what will happen to delta Y? Delta Y will be unchanged. Okay, so you think that delta Y is equal to Qy L square by 3. Okay, that is happening only when P delta effects are ignored. If you consider P delta effects, then delta Y is not Qy H square by 3. Okay, plus something. Okay, so what is the net result of this? If I plot Q versus delta in the first case, it was like this. When I am not considering P delta effects, this is Qy, which is equal to My by H, and how much is this? Okay, and this will be how much? Let me consider some strain hardening also. So this is NU, and how much is this? Delta U. Okay, which you can say as m by L square by 3 EI plus theta P into H. Now when you consider P delta effect, what is going to happen? Delta Y is not changing. So this delta Y will be unchanged, but the my will reduce. And how much is this reduction? P delta by okay, I'm doing it in force, so this will be P delta by H. This much reduction will happen. What will happen after this here? Will it be same? Same reduction will be there. It deforms further. Okay, after that it moves like a rigid body. Okay, this angle is theta p. Okay, this is your delta U. So what will happen to the Q? Now Q will be QU minus P into delta U by H. So this difference will increase, and this reduction here, this will be P delta U by H. Suppose strain hardening was not there. The original without P delta, it was like this. So what will happen? It will be like this. This will be you can think it like this, that the original curve you have rotated in this direction, and this rotation has occurred by an angle which is equal to P by H. So this rotation here, this is P by H. Yes.
Sir, the slope is changed.
Which slope?
Is due to the P by delta.
Right.
So EI has been increased, so delta Y will also.
Slope doesn't mean, change of slope doesn't mean that EI has to change. Okay. It is stiffness which has changed. Okay. Stiffness does not depend only on EI. So this is also called, this is one of the geometric nonlinearity. In nonlinearity problem means what? Nonlinearity, when we say, what does that mean? It means that the stiffness does not depend only on EI. It changes. Okay. This is another thing here that you can see that the change, the stiffness is, the relationship is still linear. Okay. Between Q and delta, the relationship is still linear. But the stiffness is not based on EI alone. In addition to that, you can see that here, the relationship between Q versus delta. So you can see that the stiffness does not depend only on EI, it also depends on P by H. So this is due to the change in the geometry. That's why we call this geometric nonlinearity. But this is only one component of geometric nonlinearity. One of the geometric nonlinearity components. Don't think that this is whole of geometric nonlinearity. Okay? And you remember how to consider that? In case of linear structures, we discussed that stiffness matrix can be derived in presence of this axial force. What is the effect of this axial force on stiffness? If you recall from the previous semester, what was the effect of this P on stiffness? The stiffness increases due to P delta effect. You have seen under the same displacement, the same force, the displacement has increased. So the stiffness reduces. And in fact, at a particular value of P, the stiffness became negative. Okay, the stiffness became 0 and then it became even negative. Two values of P I have given you, one very high, one very small. And you have seen that at very high value of P, the stiffness becomes negative. What does that mean? The stiffness is negative. You are applying force towards right and the displacement is occurring towards left. Is it possible? How do you define stiffness? P equal to K delta or stiffness matrix K11 or Kij. How do we define? But is direction coming into picture somewhere? Force required where? At ith degree of freedom to cause unit displacement at jth degree of freedom. Okay. So when we are saying degree of freedom, suppose I am saying Kii, the diagonal element. So force required along ith degree of freedom means in the positive direction of I to cause unit displacement. Now think of this, if I calculate this force in the direction of this degree of freedom 2. So I want to give a unit displacement here and it is subjected to very large force. And I want to give a unit displacement here. What I have to do? In which direction the force will be required? Upward or downward? Upward. Okay. Now think of this. I have made it vertical. Then you will be able to understand it better. And I apply a very high force P. Which direction the force will be required to make it stable? If this force is very large and you give a displacement here, then it will go on deforming and fail. So to prevent that, you have to apply a force in this direction. Okay, so that this Q into Q into L, that is giving the moment in this direction, plus P into delta. Okay, this is equal to L. So if P is very large, P into delta is very large. Okay, so Q you have to apply in the other direction, otherwise it will fail under P itself. The value of My will be exceeded due to P itself. So if this force P becomes very large, this is what we call buckling.
But to achieve that, the force Q is also large and the L length is more than the delta. So
Sorry, I couldn't. To reduce that force,
we have applied the Q. That Q will also be large.
Right.
Quantity at Q into L is more than the P delta because there is more displacement and length of it.
So large.
But
large is not equal to large. Okay, large P, let us say I take P 10,000 kilonewton. So Q will also not be 10,000 kilonewton, it can be 8,000 kilonewton, then also it is large. So if it is 8,000 kilonewton, so let us say delta is 10 mm and P is 10,000 kilonewton. So how much will be Q? Q will be equal to 10,000 into 10 to the power 3 to convert this into Newton into delta, that is 10 mm divided by 1000 to convert into meter, okay, into 3, let us say height of the column is 3 meter. So that will be value of Q. How much will be that? 100 divided by 3, so 33 into 10 to the power 3. So you can calculate how much Q will be required. But actually you will require Q in the reverse direction if you want the displacement equal to 10 mm. Otherwise you can't give 10 mm. As soon as you will give a little displacement, actual displacement will go on increasing. If you are not applying any Q and you want to give a displacement, as soon as very little displacement you will give, it will go on deforming and it will fail.
Because of P delta is a radius.
So this is geometric instability. Okay, our system will become unstable. You can see it here also. What is happening here? You can see that once it reaches this value, the new value of qy dash, with P delta effect, you have to reduce Q. If strain hardening is there, that can take care of this to some extent. But if strain hardening is not there, you can see that beyond that our system will become unstable. So P delta can lead the structure instability. And we will see later that in most of the cases, actually the failure will occur P delta, not because of delta reaching delta U. Before delta reaches delta U, the P delta effects become so large that the structure becomes unstable and it fails. Before that. Okay, so this P delta is the most important component of geometric nonlinearity. Okay. In addition to this, there are other components of geometric nonlinearity. Okay. For example, just to give you an idea what this geometric nonlinearity means, suppose initial degrees of freedom which we defined in the last semester. Suppose I am giving a moment along the degree or a rotation along degree of freedom 3, okay, or if you recall the stiffness matrix, this is 1, 2, 3 up to 6, 1, 2, 3 up to 6, okay. Element K13, how much was that? You recall? K13? The force required along 1 to cause unit displacement along 3, and all other displacements have to be 0. That was the condition. So how much was K13? 0. Okay. Suppose how we were obtaining this? I was giving a unit displacement along 3. All other displacements were 0. This was unit displacement. Okay. And then I can see that no force is required here. But is it true? this is fixed length, and you bend it. So this length, is it same as this? Suppose this is L, this is L dash. So are L and L dash same? Which one is longer? So actually what will happen, when you are giving it a deformation here, there will be some reduction in the length. It will shift inside.
If you take the deformed profile is not there.
Huh?
If you take both the ends, the deformed profile is not there. If it is fixed, then it's something like that.
We have given a rotation here. So originally my support was like this. I have rotated the support itself by a unit.
Rotation to member or rotation?
I want to give my member and a rotation. How will I give member and a rotation? I have to somehow clamp it, hold it, okay, and then I have to rotate it. Then only I can give it a rotation. So let us say initially why I have represented fixed is because I want to keep all other displacements 0. This is very important by defining stiffness, that the force required along degree of freedom I, okay, to cause unit displacement along J, when other than J, all displacements have to be 0. Only J displacement should occur, no other displacement. So if the displacement is small, if this is small, you can say that L and L dash are same. If this displacement is small. But if this displacement is large, then you can see that there will be a little displacement, and you have to make this displacement 0. So what you have to do? You have to apply a force, or a force along one will also apply.
Sir.
This is large displacement. Okay. Here we have not considered, in P delta we have not considered this effect. In P delta we have considered effect of axial force only on the lateral shear. But in reality, each degree of freedom will have effect on the other degree of freedom. When we are considering large displacement or full geometric nonlinearity, then all the degrees of freedom are related like that. Okay. That is, so when in your software you push the button for large displacement, it takes into account all these.
Sir.
Yes.
K is not equals to 0 large strain and the stiffness.
Sorry?
In large displacement, the K1 is not equals to 0 and the stiffness change.
K
1 is not equals to
not equal to,
and
that will be
stiffness
not
will
equal.
change. That's why it's so right.
Sir, these given due to degree, these are the degrees of the freedom. It's kind of indeterminacy. Ki.
Kinematic?
Indeterminacy. Ki. These are the Ki.
Uh-huh.
Now I want to find the forces generated along the other stem when I will displace one. Then if I am giving displacement along this Ki rotation, I will displace like this. I will fix other end. This is I fix. This is I have pin. So this direction tops. This direction stops. Due to this, and so it should be like this. It should not be like pixel rotated like this.
Both are the same thing, because you want to give a rotation here.
Yes.
How will you give a rotation? At the fixed end, at the pin end, how you are going to apply a rotation?
Applying moment.
Moment. How will you apply moment?
Taking lever arms.
Lever arm. Okay. That means you will be bending something here, and you will be rotating this.
Yes.
That's how you can apply.
Yes.
So it is same as having a fixed hand and rotating this fixed hand. Both are same. So you take a pin support and give a rotation, but here we are not going into the details how to give a rotation. Okay. Or you consider this as the fixed and rotate the support itself. So then you can see that this angle will be same as this angle. So both ways it can be written. Sometimes we show it like this, and sometimes we show it like this. Both are same. Okay? So we are not teaching you here geometric nonlinearity. Actually, we are discussing in the department to have some pre-PhD courses. Because the problem is that when PhD students are with MTech students sitting there, many things we have to stop. I mean, we cannot go into the full details. There is a limit what we can cover in a semester. Okay. So there should be some courses beyond MTech, which should be there for PhD students. And this is one of the topics, geometric nonlinearity. Okay, we are not classifying. Similarly, in nonlinear seismic analysis also, more topics are here, which needs to be, what we will be covering here, we will be mostly limited to pushover. Nonlinear time history analysis, I will give you a little introduction, but we will not be able to cover that in more detail. But now, the research has developed quite a lot in the last 10-15 years. We have to look into nonlinear time history analysis. Okay, so where to cover that? MTech courses are limited. We can do that one only. Okay, so we are thinking of some pre-PhD courses. Those MTech students who have done, those PhD students who have done masters here itself, they will be able to take those courses in the first semester itself. But those PhD students who have taken somewhere else and might not have done those courses which you are doing here, MTech courses itself, they will do those courses in third semester. First and second semester, they will do with MTech students these courses which we are teaching here, and third semester those pre-PhD courses. So one course we are planning in advanced numerical analysis. Okay. Another we are planning one course on experimental methods also, because now we are doing a lot of experimentation also, so we should know how to do it. Our PhD students should be exposed. So those courses we are planning hopefully to run in the next session, and that will be better. Okay. Similarly, one course on continuum mechanics, that is very much necessary for PhD. MTech students, I think optional course is there. I don't know whether already we have a course on quantum mechanics or not, sorry, continuum mechanics or not. But in soil there is one course on constitutive modeling, which is very close to continuum mechanics. So one course we are planning on continuum mechanics for PhD students. Okay. MTech students, if anybody is interested, can take in third semester. If anybody is interested. So that will be theoretically open, but I know not many MTech students will be doing that. In case any MTech student wants to do PhD, then in any case, he or she will be doing it in the first semester of PhD. Okay, so that we are thinking. These aspects we will cover there. So this large displacement or geometric nonlinearity is more effects in addition to P delta. P delta is the most important effect because these effects are not so large as this one. This is very large. This cannot be ignored. Okay. So P delta, and this can be taken care of very easily. Okay. This type of effects in some of the structures we have to take. Okay. So that we will learn. We will not cover in this course, but maybe in pre-PhD course we will cover. Okay. So this is about one member. Let's think about the building. Yes.
Sir, when I'm applying speed, this delta is due to this delta there is some bending moment called Z as well, right? So this delta I'm not, as you said, this delta I'm not accounting because my delta y is not changing. My
I couldn't. What was
delta
saying? My my will remain same.
My will remain same and delta
Okay.
y will not change.
And my remains same. So my phi y will remain same. For a section, the phi y is same.
From equations we got that.
Right.
But in reality, when the load will act,
Yeah.
there will be some deformation as well.
Yes,
that-
deformation will occur.
And when-
So, if the deformation is less than yield, okay, then you can see, suppose I apply this much force. Oh, I'm sorry. Suppose I apply this much force. You can see that with period type facts the displacement has increased. So displacement will increase. But the yield force or the displacement at yield, okay, that will remain same because the force will also reduce in the same proportion at which it is going to yield. Because yielding will depend upon the capacity. P delta is because of the applied force. P is applied force. Okay. Capacity will remain same. So due to applied force, the displacement will increase. Okay. But the capacity cannot increase. Capacity will remain same. So the capacity at which it is yielding, that will remain same.
But sir, that P delta effect, that delta, that is not coming in my, that is coming.
Delta Y is not the applied force. It is not action. It is capacity.
Right.
So this cannot increase. But the displacement at any given force is going to increase. Both are true. Okay. The displacement is increasing, but the yield displacement is not increasing.
But when I will design any structure in displacement based design, that P delta effect is never going to come.
Why not? I will consider.
Because I will see my capacity curve for that, and my
Displacement based design doesn't mean that I will not consider the forces. Displacement design only means that I will control the displacement. But the forces will be there also because the displacement will be coming because of the forces only. Okay. So displacement based design doesn't mean that I will design just delta y and I don't need the forces. I will require forces there also in displacement based design also. Which forces are causing that much displacement? That I will require.
So sir, because of P delta effect, we require less lateral force to cause twinning.
Or, in other words, our structure can resist less forces.
Yes.
Okay. Now my structure will reach its yield and ultimate capacity at much lower forces. So the capacity of the structure has reduced in terms of forces. The capacity of the structure, this particular cantilever structure, in terms of My is same. My has not changed. But its capacity in terms of lateral load has reduced.
And sir, this P is coming because we have designed the column, the capacity of column.
I am coming to that. So far, I have given you this problem. This problem I have given you. Okay. But in real building, will there be only lateral force? There will be gravity load also. Due to dead load and live load. So there will be some gravity force also. What will be the effect of these gravity forces? One effect of this gravity force will be that there will be bending moment diagram. So, sorry, there will be bending moment in our dimension form. Okay, so one effect will be this, that the bending moments will generate. And when the bending moments generate, the total, out of total moment capacity My, part of the moment will be consumed by gravity itself. Okay. Secondly, because of this, there will be axial forces in the columns. Suppose this is W, so there will be WL by 2, WL by 2 and WL by 2 from the other side. So how much is the compressive force acting in this column? Can you tell me? 2WL. WL by 2 from left, WL by 2 from left, and same coming from the upper. So 2WL force will be acting here. What about this column? How much force will be there? Okay, so like that you can distribute the effect of gravity force on axial load in the power. Okay, so I told you that there are two effects. One effect is the bending moment, another is axial force, which will cause P delta. Okay, so here in this tutorial we are focusing only on P delta. This effect of the gravity load, because it is distributed, we are not considering. So essentially what we are considering is this. Let us say it is P, 2P, P, P, 2P, P and so on. So when you will be considering this assembly, in addition to this Q, you will also consider the force of force. You agree? 4P or 2P? Actually, as we have done earlier, 2P will be coming in reality, it will be 2P here and 2P here. So, bottom column will be subjected to 4P, the top column will be subjected to 2P. You can consider that. Okay. Or, just for simplicity, the whole assembly we will subject to 4.
So because of the lateral force, this P is coming, or this P is because of
Sorry, because of axial force?
this P is coming with gravity load, or because of the lateral force, this P?
Both actually.
Both.
Both will work. But due to lateral load, what will happen? Here it will be tension and here it will be compression. So it will reduce the effect here, it will increase the effect. So more or less it will be compensated. So in many cases what we do, the P delta effect due to earthquake force, we ignore, and we consider the value of P under gravity load itself. Okay. Now let me ask you, will there be any effect of P delta on period of a structure?
Yes. Thickness is changing, so temperature will change.
So even the period of the structure is going to change. So if you put gravity load, okay, on the structure, its period is going to change. So for calculating the period, you need stiffness. For calculating the stiffness, you need P. So which P we should use? There we consider gravity itself. So in case of SAP and ETAPS, there is a procedure, okay, where what you do, first you consider, and this P delta is a nonlinear analysis. P delta, when you consider P delta, P delta is active only in nonlinear analysis. In linear analysis, this command is not active in the software. Okay, so first you perform a nonlinear analysis under gravity load. And when you are doing nonlinear analysis under gravity load, no hinges are forming. Okay, our structure has to remain elastic during gravity load. So it is not yielding. No hinges in any beam or column will occur. Okay, but still you have to carry out a nonlinear analysis. Okay, results will be same whether you perform linear analysis or non-linear analysis. You perform a non-linear analysis. Only difference is that in non-linear analysis it upgrades the stiffness for all non-linear effects which we have considered. Here the non-linear effect we are considering is P delta. So it will upgrade the stiffness when you perform non-linear analysis. In linear analysis, the stiffness is constant. It does not change. In non-linear analysis, the stiffness gets upgraded, okay, for the axial force P. So when you perform non-linear analysis, the stiffness will be modified, okay, for P delta effect. And then you perform eigen value solution using this modified stiffness. Okay, then your period of the structure will be some little bit longer. Okay, stiffness will reduce. So P delta effect causes a reduction in the stiffness, hence elongation in the period. Okay, and under any given force, it means larger displacement, and it also means that the yielding will occur now at lower force. And when we are talking in terms of earthquake, there is no force. So what does that mean? It means that it will occur under lower PDA or lower SA. So yielding will occur under lower SA. Ultimate, that means collapse, will also occur under lower value of SA. Lower intensity earthquake, my structure will collapse when we are considering P delta effects also. And we cannot ignore P delta effects in case of earthquake error. Okay. In case of gravity load, even if there is a sway, we can ignore. That is small. But under earthquake force, we can't. We have to consider P delta analysis in all our analysis. Okay. Especially when we are talking about performance-based design or displacement-based design, where the displacements are larger. We are going into non-linear plane. So displacements will be larger. There P delta effects cannot be ignored. Other geometric nonlinearity effects we can ignore. Usually in design people are ignoring those. That's why we are also not teaching those you here. But P delta effects you can't ignore. P delta effects you have to consider, and that's how you will consider. So because of this P delta, this 4P acting here, let us say, what will happen to the Q versus delta for this assembly? Can you plot the Q delta? Suppose hinges are forming here itself, MBY. So earlier you have calculated QY in terms of due to P delta effect. What will be the difference if there is a force acting on the column? So this column is deforming like this. So this 4P will be acting here. Our beams are deforming like this. What will be the effect of this? If now you are taking the moments here, okay, this R, this will remain same. Why? Because it has to be MDY over L by 2. So R will remain same. What will happen to the Q or QY when these hinges are forming here? If you are taking moment, let us say about this point or about this point, let us say about this point we take the moment, then QY into H, okay, that will be equal to R into L minus 4P into delta. Summation M equal to 0. Because additional clockwise couple is clockwise moment is there because of this 4P. 4P into delta. This is our delta, and at the time of yield, this will be equal to delta.
So why did you say that R will be constant because it will be modified because of the scale P delta?
At yield, how much will be the force? If it is yielding, then this has to be equal to MVy. And if this is MVy, then this will be MVy by L by 2. At yield. Okay, what you are saying is at any other instant. Okay, but at yield, this R has to be MVy by L by 2. So you can think it like this. At a given force, the displacement will increase. At given displacement, the force will decrease.
Sir, there will be one additional moment, 4p into delta. That delta is delta y plus column.
No, it is total. The delta y is delta by plus delta cy. Both are included. Okay. So that change will be there in your individual assembly. And this change is same as if rotating this curve. Suppose your original assembly curve is like this. Without P delta effect, it was like this. After P delta effect, what is going to happen? Let us say this is delta 1, this is delta 2, this is delta 3, this is delta 4. Somewhere. Due to P delta effect, what will happen? Okay, this rotation is P by H. So this much reduction, so this will be P by H delta 1, this will be P by H delta 2, P by H delta 3, P by H delta 4. This much reduction will take. This will happen in case of assembly. Suppose you are doing this multi-story building with rigid floors. What effect it will have? What effect P delta will have here? Let us say this is delta 1. This is delta 2. So suppose hinge is forming here, or let me say the hinge is forming. So at that yield, how much will be this force? Or let us say occurring at both the ends for the time. Let us assume. So hinge is forming at both the ends. What will be this? The capacity here was M, here also it was M, and it is yielding. So what will happen to this Q1?
M divided by H by 2.
M divided by
H by 2.
h by 2, that will give you q1. What about p delta effects? Minus p and 2p, okay, divided by h into so this will be additional effect. So ground story displacement will also increase, the top story displacement will also increase, or the forces will reduce. So the force will reduce. In the ground story, the force will reduce by this amount. In the top story, it will be reduced by P by H.
So we can do this in this way. We can calculate delta and for the without considering the delta effect. And using that data, we can modify our
Or when you were calculating DCR, for calculating DCR, let us say this is 0.1, this is 0.2, 3, 4, 5, 6, 7. So what you are doing? First you are calculating the moments. No? For calculating DCR M1. So how much will be M1? Q, 2Q. So 3Q divided by 2, if EI is same, otherwise it will be distributed in proportion. Okay, so 3Q by 2 into H by 2, okay, plus
But sir, the delta is unknown.
right.
So how can I compare demand to capacity ratio?
You have to use compatibility, or as I told you, you rotate.
in the previous
You rotate this curve by P by H. So ground story curve will be rotated by 4P by H, and the top story curve will be rotated by 2P by H. So whatever is the total axial force acting in that story, by that amount this curve will be rotated. Okay. So you try this. I am sure you will have some difficulties. We will take up those on Monday, tomorrow at 4. And there I also want to cover the effect of shear deformation. Okay. And the first problem of tutorial 3. That we will take up tomorrow. Anything else you want to ask for now? You can complete tutorial 2 now. You have to submit it